So for my project, I decided to look at a calculus approach to all of this geometry that we've been studying in the course. And I really wanted to try a technological approach because I love integrating technology into my classroom, but I'm really not that familiar with GeoGebra or that geometry sketchpad. So I really tried to get familiarize myself with it to help me with this project. And in doing so, I found a really cool application to help me prove, or at least show my students how to prove, that the limit as x approaches 0 of the function sine x over x equals 1. Now this is something really difficult for my students to wrap their head around in my calculus courses, because usually up to this point where we start to introduce this trig limit, we've discussed how we can use direct substitution to help us solve limits. We've discussed how we can use factoring to help us solve limits. And usually factoring is most likely used when there is an indeterminate form or a hole present within the function that we're dealing with. And you can kind of see how we're going to get that here, because if we substitute in 0 into our function, we're going to get 0 over 0, which is that indeterminate form. Now typically factoring would work nicely if we were given some polynomials, because eventually we'd be able to possibly cancel a factor out since we're dividing, and we'd be left with something that direct substitution would work for. But since we're dealing with trig function here, we can't really factor the numerator or the denominator, so how on earth do we get around this hole that we have here from the direct substitution of 0 over 0? Now, there is a nice application using geometry to help us prove why this equals 1, and that's what I'm going to do today using my geometry sketchpad, or sorry, my GeoGebra knowledge. So what we're going to do is, to help us prove that this limit equals 1, we're first going to construct a circle. Now, bear with me as I use some of these different applications on GeoGebra here. I'm still kind of learning, but I think I've practiced this enough that I know what I'm doing. So we're going to create a circle through a particular point. So we'll call that our circle. And I want to make sure that this is going to definitely resemble the unit circle, so I'm going to try to make it as uniform as possible. Maybe we'll make it a little bit bigger. There we go. Alright, so we're going to assume this is our unit circle, so from the center of the circle to the edge, we'll assume that that distance is 1. Now, from here, we're going to do a little construction. We're going to form a tangent line through this particular point. We're going to assume that this is kind of the initial side of an angle, the x-axis, if you will. So we're going to form a perpendicular line through this point and this curve. Let's try that again. We're going to go through this point and that curve. If it'll work for me. Oh, I think I know what I need to do first. Let's create a chord, let's say. Not a chord, segment, radius. There we go. And now let's try a perpendicular line. There. Okay, so tangent. Notice how if I want to move this point around, that tangent line will always be touching the circle exactly 1 point. Right, so there's our radius of 1 because we have a unit circle, and then we have our tangent. Next thing we're going to do is kind of construct another segment through the radius to any point on the tangent line. There we go. So we're going to kind of form this triangle. Notice how this is a little different than the triangles used in the unit circle, because our triangle is going to the line of tangency, not to the edge of a circle. But we are going to put a point there, right where where the unit circle and this segment intersect. So let's go ahead and throw in that point. Now where's there we go. Intersect. Right there. And what we're also going to do is form another radius, or not a radius, this time it's a chord, from this point of intersection to this point of tangency. So we'll create another segment. In this case it's a chord. There we go. So in all this construction, notice how whenever I move this point on the line of tangency, the shapes of these different triangles changes. You can go as far up as you want, you can go as far down as you want, but notice how everything kind of stays uniform as you move that around. What we're going to do in this construction is we're going to use this idea of movement, and I'll come back to this in a second. I want you to notice how we have three basic shapes going on here. The first one, and I'll try to highlight them, the first shape we're going to focus on is this small triangle within the unit circle. The second shape we're going to focus on is this sector, and I'll try to make it different colors so you can see it. So the sector is kind of like a piece of pizza where you go all the way to the crust. So the crust is kind of the edge there, if you will. So we have the small triangle within the circle. We have the sector that goes all the way to the edge or the curvature of the circle. And then the last shape we're going to focus on is the large triangle, which goes all the way to that tangent line. Okay, so hopefully those different colors will help you visualize these three different shapes that we're going to use. Alright, so let's go back to this idea here. How can we use this geometric construction to help us prove this trig limit? Well, what I'm going to do is try to redraw basically what we had going on there in GeoGebra. Horrible, but bear with me. Okay, so we're going to say this is our unit circle. This is our distance of 1. This was that special point on the x-axis that we drew our tangent line through. And then we drew this segment to the tangent line up there. And then we had this other chord connecting those 2 points. Okay, so that's basically what we had on our GeoGebra. What we can do is label some other things going on here. We definitely know that this is a radius of 1 because it's a unit circle, but notice how this point right here, since it's on the unit circle, we know that that has a coordinate of cosine x, comma, sine x. Assuming that this angle right here we'll say is x degrees or radians, we'll just call this angle x. Now the other thing that we can do is label in terms of the big triangle what this height would be. So let's maybe label this y, and we want to figure out what y would be equal to. So notice how in this triangle, since this is a tangent line, we know that this is a right triangle. We could use some trig functions to help us figure out a value for y. Or maybe not a specific value, but a different label for y. So in relation to this angle x that we're focusing on, notice how y is the opposite side, and 1 right here is the adjacent. So we could use the trig function tangent of x would be y over 1, which is just y. So instead of labeling this as y, we could label this as tangent of x. So in this construction, now that we have these three different shapes, the two triangles in a sector, we're going to analyze the areas of these different shapes. Okay, so two things that we have to know, since we definitely have two different shapes here, are the areas of a triangle, which is a 1/2 base times height, and we also need to know the area of a sector, okay, the area of that piece of pizza. Well, that's simply the angle divided by 2 pi. Okay, in this case we're working with radians. So the angle that you're focusing on out of the entire circle, and since we're wanting to find area, we're going to multiply that by the area of a circle, which is pi r squared. So we're going to use these two different areas to help us figure out the areas of these three different figures. So let's first find the area of the small triangle, which was the one inside of the circle. We need 1/2. The base is 1. But then we got to figure out the height. Okay, the height is coming from this altitude right here. So we got to figure out how high this triangle is, and notice how the height of that triangle is determined by this particular point. And since this particular point has this particular ordered pair, we know the height of this point is the y value. In other words, it's sine x. So the area of the small triangle can be represented by sine x over 2, doing a little simplification there. Next, maybe we'll check out the area of the sector. So that's our angle, in this case x, divided by 2 pi. and we're going to multiply by the area of the circle, which would be pi, and then the radius of the circle we know is 1 because it's our unit circle. Doing a little simplifying there, we get x over 2. And then the area of the big triangle, okay, the one on the outside formed by this tangent line here, we need 1/2. Again, the base is still 1. And the height, since it's a right triangle, we'll use this leg. Okay, height is a y value, but over here we determine that the y value is the same as tangent of x. So we have tangent of x over 2. Okay, so we have all three of these different areas. What's nice about using this GeoGebra illustration here is to help the students visualize the connection or the relationship between these different areas. Notice how if I move this point further away, clearly the area of the blue big triangle is greater than the area of the sector, okay, that green figure. And that sector area is still bigger than the area of this red triangle within the circle. So that's pretty obvious. But notice how as we drag this point closer and closer and closer and closer, the areas start to become the same. Okay, notice that the difference in areas between the three figures is much greater here, but the closer we drag this point to this beginning point, the areas start to actually become the same. Okay, almost negligible, and if we line them up on each other, all three areas happen to be 0. So all three areas could be the same value of 0, but notice how it also depends on how far away they are, because eventually the big triangle will have more area than the sector, and the sector will have more area than the small triangle. So you can see how we have this kind of inequality happening here because the areas could be the same depending on where this point is located, but clearly the areas would not be the same if it's further away because we have a large difference in area. So using that idea, we can form an inequality statement using these three areas here. So we could have the area of the small triangle be less than or equal to, because remember they could be equal to if all three areas were 0. Clearly the area of the small triangle is going to be smaller than the area of the sector, and even that's going to be less than or equal to the area of the big triangle. Okay, we can see that by the connection in the GeoGebra construction. So filling in the different values we had sine x over 2, which would be less than or equal to x over 2, which is less than or equal to tangent of x over 2. Just substituting in those area values that we just found. So let's continue from here. Now remember, let's not lose sight. The whole idea is to figure out the limit as x approaches 0 of sine x over x, and somehow we want to prove that this equals 1. Okay, this is our goal. Alright, so let's see. All these are being divided by 2, so using some algebraic techniques, if we multiply all these by 2, that's clearly going to cancel all the 2's out. So we'll be left with sine x is less than x, which is less than tangent of x. And let's see, this is kind of the step that confuses students, but again, if they understand this idea of multiplying everything by 2 to cancel some things out, let's go ahead and divide everything by sine x. And I try to tell them the reason I'm doing that is because if this is the function that we're trying to find the limit of, we want this to kind of show up somewhere within this inequality. And notice how that's kind of showing up here. Eventually we're going to find the reciprocal of it, but it's starting to show up. So simplifying from here, we'll have 1 is less than or equal to x over sine x. Then using a little trig identities here, or simplification, tangent of x over sine x can be rewritten as 1 over cosine x. So now we're getting somewhere, but notice how this does not match our function exactly, so what we could do is reciprocate it, but if we reciprocate this one, we have to reciprocate the other ones, and we also have to reciprocate the inequality symbols as well. So reciprocal of 1 is just 1. The reciprocal, or I guess flip if you will, of the less than or equal to would be greater than or equal to. We'll flip the middle term, we'll flip the next inequality symbol, and we'll flip the last term. So now that this function matches the limit one that we were trying to before, let's go ahead and take the limit as x approaches 0 of this entire inequality statement. Meaning if we take the limit of 1, we got to take the limit of them all. So up to this point, my students would know that the limit as x approaches 0 of 1, the limit of any constant is just that constant itself, which is 1. We don't really know what this limit is, so we're going to leave that value or function alone. Okay, this is what we're trying to figure out. We don't know what it is. But what we can do is figure out the limit as x approaches 0 of cosine of x. Notice how direct substitution would work in this case. Cosine of 0 is 1. So what we have forming here is something called the squeeze theorem. Okay, my students always like the name of that for some reason, the squeeze theorem, because based on this inequality statement, okay, if this is the limit that we're trying to prove, notice how the greatest value it could possibly be is 1, but the smallest value it could possibly be is 1. So if it can't go bigger than 1 and it can't go smaller than 1, that must mean the limit itself must be 1. You can't be more than it, you can't be less than it, so that means you must be equal to it. So this is what's known as the squeeze theorem. Okay, you're trying to trap your trig function between two known values that happen to be the same value, that way you know you're equal to it. Okay, so that's something that I normally do by hand with my students, and it's really difficult for me to get them to visualize this whole triangle circle thing, moving this point up and down. It's really hard for me to do that doing the construction on the board. So that's why I really wanted to try to do it here in the GeoGebra, and notice how I think this is a much better visual representation for them to see how the areas change by moving that point back and forth. Clearly all three areas are different here, but notice how as we move it closer they start to become the same, so we get that inequality relationship between the different areas. So I hope you like my presentation. I think actually, I know I plan on using this next year just because of the ease of it and the better visual representation. But hopefully you guys, if you teach calculus or want to blow some of your students' minds, go ahead and show them the squeeze theorem. I'm sure the calculus teacher would appreciate it when your students ever get to that level.